Welcome to lecture 19 of the course. It is lecture 9 of the second module. In this lecture, we will continue our discussion on Transmon, and then we will start discussing a very important topic called quantum dissipation or noise. Quantum dissipation or noise is extremely relevant for all practical quantum circuits or quantum devices. So let us begin. In the last class, we continued our discussion on Josephson element from the previous one, where we learned that the Josephson element is a nonlinear inductor with inductance given by this expression. Here H is the Planck's constant, IC is the critical current, and cos phi is the term where phi is the phase difference across the junction. And then we went on to discuss the energy operator, and energy operator we expressed in terms of the number state basis or the Fock state basis, and where this operator n cap, it's an operator whose eigenstates correspond to macroscopic state of the circuit with a well-defined Cooper pair numbers. N refers to the Cooper pair numbers, and Ez is the Josephson energy. This Hamiltonian, this form of the Hamiltonian is similar to the one that we discussed in the context of Cooper pair box Hamiltonian in a previous class in this module. And this Hamiltonian can be written in terms of phase difference across the junction phi, where this function phi can be treated as an operator, and we can define a basis state phi cap, which can be expressed in terms of the number state basis, or inversely we can express this number state basis in terms of this phi basis. And using all these things, it turns out that if we define the operator e to the power I phi cap to have this particular form, then this Hamiltonian can be written in a very compact form, that is Hj is equal to minus Ez cos phi cap. Now phi cap is the phase conjugate of the number operator, so necessarily they satisfy this commutation relation. Now there are two things I mentioned. One is that the Josephson element, this term is actually referred to generally to understand nonlinear. By this we actually mean that we are talking about nonlinear inductance. On the other hand, when we say Josephson junction, this basically refers to physical realization of the junction. Now Josephson junction is a nonlinear inductor in parallel with a capacitor, and this is represented in this symbol, by this symbol. Whenever you come across any symbol like this, you should understand that this is referring to the Josephson junction. Then we went on to discuss superconducting qubits, and these are extremely important because they are artificial two-level atoms, very relevant in the field of quantum information processing. Now a circuit composed by Josephson junction has this form of the Hamiltonian, where this one is the charging energy and this is the tunneling part of the energy, and this we can express in terms of the number of Cooper pairs also, because you know that Q is equal to twice of the elementary charge into the number of Cooper pairs, so we can express it as a two energy coefficients are appearing here. One is the Josephson energy and another one is the charging energy. By the way, here this actually phi refers to the magnetic flux and phi 0 is the flux quantum. This particular thing I did not mention in the last class, that this phase difference, you see initially we express this Hamiltonian in terms of the phase difference across the junction, and it can be shown that this phase difference is related to the magnetic flux via this expression where phi is equal to 2e by h, which is related to the flux quantum. You know the flux quantum phi 0 is equal to h by 2e, and phi is this is the magnetic flux. So, and maybe we'll do this in a problem solving session, and this maybe I will explicitly show it. Now the superconducting qubits are classified according to the ratio between this Josephson energy versus the charging energy and to the variables by which they are controlled. In this context, we briefly discussed about the charge qubit and the Cooper pair box qubit, where naturally, because it is charge qubit, the charging part of the energy dominates over the Josephson part of the energy, that is the flux energy. And symbolically, or the circuit diagram for a charge qubit is of this type. And as you can see that this kind of qubit can be controlled by electric field, because ultimately charge dominates here. On the other hand, the flux qubit case, we have this Josephson energy Ej is greater than the charging part of the energy. And this is basically a superconducting ring interrupted by 1 or 3 Josephson junctions. And the flux actually induces two circulating superconducting currents, one going in the anti-clockwise direction, other going in the clockwise direction. So this forms the two states. And then we briefly talked about phase qubit, where a single Josephson junction is connected to a current source, and in this case the Josephson part of the energy is much greater than the charging part of the energy. Then finally we discussed in somewhat details about the Transmon qubit. Physically speaking, a physical picture was given. We discussed about it, that it basically consists of two metal pads, metal pad 1 and say metal pad 2, connected by a nonlinear wire or a nonlinear inductance. And to discuss it, we briefly revised what we learned about the quantum linear LC harmonic oscillator, and we utilize these things in later part. And also I have discussed about a scanning electron microscope image of a real Josephson junction. There is no need to go into the great details, but thing is that there are two metal, say metal 1 and metal 2, and they are overlapping each other, and they form a kind of a gap or junction is there, and they are widthwise each of the metal is around 200 nanometer in size. Details doesn't matter, only thing what matters is that we have these two metal pieces and they form a gap between them, very tiny gap. Okay, and then this can be represented by this diagram here, this terminal 1 for metal 1 and terminal 2 for metal 2, and then they form a junction. And magnetic flux is change in magnetic flux is the important factor that we have to keep in mind. And this element can be, its energy function can be described by this particular expression here. You see, what matters is only the change in the magnetic flux. And this, when we expand this cosine function, it can be shown that this energy function of this Josephson element can be written into two parts. One is the linear part and one is the nonlinear part. And it turns out that the linear part basically refers to the energy of a linear inductor, and this refers to the nonlinear part, and which is extremely important. And recalling that the linear inductor, we know the energy in a linear inductor is magnetic flux square divided by twice L. So this allows us to make a correspondence, and thereby we express the Josephson energy as a magnetic flux quantum square divided by Lj. Lj is the inductance. And then we discussed, then we wrote the total full Hamiltonian for the Transmon qubit. So we have this charging energy part and this the potential energy part. And if we actually plot the potential energy part here, this cosine function, if we plot as a function of reduced magnetic flux, that is phi j by phi 0 across the Josephson junction, then we get this particular plot here. You see, this particular one, gray one, refers to that cosine potential. And in fact, if we break it into linear and non-linear part here, as you see, this is the linear part and this is the non-linear part, and linear part is drawn here. This refers to the this is the linear harmonic potential, phi j square by twice Lj, and this cosine function is periodic in pi. So if our magnetic flux value is close to 0 or very small, then this whole potential can be termed as the linear. So if we deviate much from it, then the non-linearity has to be taken into account. Okay, and then we discussed that as we after dividing it to linear and non-linear part, linear part already we studied in great details throughout the course. So linear part, if we write in terms of the annihilation and creation operator, that is simply h cross omega 0 a dagger a. On the other hand, non-linear part can be expressed in this particular form in terms of creation and annihilation operator. Then taking this phi 0 point fluctuation, okay, this is reduced fluctuation, quantum 0 point fluctuation, to be much smaller, which is a realistic approximation, than under rotating wave approximation, where we have dropped all the rotating terms and only keep the non-rotating terms. This particular Hamiltonian under rotating wave approximation can be written into this very simple form, and this is what we are going to discuss today in our initial part of this course class. And as you see, this first term is particularly interesting, where it basically shows that the harmonic oscillator frequency, there is a shift by delta q, and this is the so-called Lamb shift, and this happens due to the quantum 0 point fluctuation. On the other hand, this term is coming due to the non-linearity, and this is what now we are going to discuss. We can rewrite this Hamiltonian in terms of number operator. N is equal to a dagger a as follows. We can write HRWA is equal to h cross omega q n cap minus h cross alpha by 2 n minus 1. So this is an alternative form of the same Hamiltonian that we have worked out here, and here this omega q is equal to omega 0 minus delta q. Okay, let me explain. The first term is obvious because simply a dagger a is nothing but the number operator, and omega 0 minus a delta q is omega cube. Now as regards the second term, by the way, the first term denotes the number of Fock state. This term basically denotes the number of Fock state we have, and it is the linear part of the total Hamiltonian. On the other hand, to get the second term, let me analyze the term a dagger square a square. Let us analyze it, then you will understand how I got the second term. So a dagger square a square, this I can write as a dagger a. Now what I will do, I will exploit this commutation relation. A dagger is equal to 1, which is I can write as a dagger minus a dagger a is equal to 1. So from here you see that I can write a dagger a is equal to a dagger minus 1, right? So therefore I will just replace this in this way, a dagger, and this would be a dagger. So this would be a dagger minus 1, and then this is a. So you can easily see that I can write it as a dagger a
minus A degar A, and obviously this is n, this is n, and this is n, so therefore I have n square minus n, which I can write as n into n minus 1. Okay, so clearly this second term is the nonlinear part of the total Hamiltonian. So what we have is this: the linear part is equal to h cross omega q n, and h nonlinear part of the Hamiltonian is minus h cross alpha by 2 n minus 1. Okay, so now let us look at some of the experimental parameters using which a Transmon qubit was realized in laboratory. You see, our Transmon, as you know, the circuit diagram for the Transmon, we have this capacitance is there, and this is the Josephson junction is there. Okay, and this has a inductance, say Lj. So this is the circuit diagram, as we all know. Or another form is that we have basically two metal pet separated, and this is connected by this nonlinear inductor here, and this is the capacitance between these two metal pads. This is say metal pad number 1, this is your metal pad number 2, and the capacitance in experiment, in real experiments are done. In real experiment, the capacitance was taken to be around say 65 femtofarad, which is extremely small, and on the other hand the inductance was taken out to be 14 nanohenry, which is again small. And then if you do the calculation, it turns out that this corresponds to the Josephson energy Ej is 50 square by Lj. It was around 12 gigahertz, and on the other hand the charging energy Ec, which is q square by twice c, it turns out to be around 0.3 gigahertz. Okay, to first order, the energy level diagram of this Transmon could be actually drawn. So let me explain it. So first energy level, that's the ground state energy, let me denote it by k0. The second energy level is say 1, and I will explain this is the first excited level, then this is the second excited level, let me represent it by 2. Let us say this is energy, let me denote it as E0, this is say E1 and E2. Now from this Hamiltonian, okay, let me just utilize this. From here you can see that the energy, okay, let me write down the Hamiltonian once again here. The RWA Hamiltonian that we have here is h cross omega q n minus, I have h cross alpha by 2 n minus 1. So you can immediately see that the energy expression for the energy would be simply h cross omega q minus h cross alpha by 2. Actually, let me, okay, if I have it, if I operate on the number state, it will be simply like this, n minus 1. Okay, taking this my energy, nth energy level. So let me find out the difference between the energy levels. For example, first excited state and the ground state energy level, you can immediately see that this would be simply h cross omega q. On the other hand, say the second energy level minus the first energy level, that would be from this expression itself you will see twice h cross omega q minus you will have simply h cross alpha, that is your E2, minus the E1 is simply h cross omega q, and this is going to give you h cross omega q minus h cross alpha. So here you see that this energy difference is h cross omega q. On the other hand, this energy difference is h cross omega q minus h cross alpha. So what you see from this energy level diagram for the transmon, I'm just considering this only 3 energy levels. So we see that the energy levels are no longer equally spaced, right? That is what happens in linear harmonic oscillator. Now because of the presence of the nonlinearity, the harmonic oscillator now becomes anharmonic, and this is what is needed to make the transmon to be used as an effective two-level system or qubit. In fact, with the parameters that we have mentioned, this omega q turns out to be around 5 gigahertz, and on the other hand this alpha, this turns out to be around 0.3 gigahertz. Now as regards the quantum fluctuation, if we look at the quantum fluctuation in the problem in this transmon with the given parameters, quantum fluctuations, what they were measured, it turns out that this phi 0-point fluctuation divided by this flux quantum was around half or 0.5, and the fluctuation in the charge, that was with respect to the Cooper pair, that is twice of the charge of the electron, was turns out to be 1.01. So what it physically it mean is that in the ground state there is, so it means that in the ground state there is about one Cooper pair, as you can see from this equation, that q 0-point fluctuation divided by 2 is equal to 1. So it means that in the ground state there is about one Cooper pair worth of charge, okay, fluctuating back and forth between the two metal pads. This is what it means, between the two metal pads. So okay, two metal pads, all right, or the two islands. On the other hand, if you look at this equation here, the magnetic flux is oscillating on the level of about half a magnetic flux quantum. So this is magnetic flux quantum. So the magnetic flux oscillates on the level of about half a magnetic flux quantum. Now typically there are on the average about, on the average there are 10 to the power 12 electrons are there. Electrons are there on the average on each metal pad actually, or metallic island, on each metallic, in fact here it is superconducting island, metallic island, okay. So in the transmon qubit, so this is actually, it is absolutely clear, and it clearly shows that why we must have to work at very cold temperature, because our device must be isolated from noise, because our quantum fluctuation is, you see, so sensitive, one Cooper pair as regards charge is concerned. So we have to keep our device at very cool temperature at very low temperature. This implies, just to avoid too much of quantum fluctuation, so we must keep the transmon at very low temperature, very low temperature. Okay. Nevertheless, we cannot completely get rid of quantum noise or dissipation, and we must know how to incorporate noise into our model. So that's why now what we are going to do, we now have to see how quantum noise or dissipation could be taken into account in our mathematical model. So this is what we are now going to discuss: quantum noise or dissipation. Okay, this is a very important issue, and we'll try to discuss it in some more details now. Dissipation or quantum noise is encountered in many situations. For example, decay of an atom. Suppose an atom is a two-level atom. If you consider, it has a ground state and an excited state. Even though these are eigenstate, ground state and the excited state, we know that the atom cannot stay in the excited state for a long time. So after some time it spontaneously decay into the ground state. Again, we can have a situation where, suppose we have a cavity, and inside the cavity the photon is oscillating back and forth, but after some time the cavity may leak away from the cavity. So photon leaking away from a cavity, that is also a dissipation from a cavity. And also there is something called decoherence or dephasing, which typically means destruction of the superposition states. Say again, we have a two-level system, and we have a superposition state like, say, Cz, this gate Z plus Ce, this gate E. This is a superposition state, but we cannot it cannot be maintained for long time. So this superposition state generally gets decayed. This decay or get destroyed, decay of superposition quantum superposition state, decay of superposition state. This is also quantum dissipation or quantum noise. It generally happens as soon as the system comes into contact with environment or any perturbation. So taking dissipation into account in a mathematical model is a non-trivial affair in quantum mechanics. To understand it, let us see how dissipation is taken into account in classical mechanics by the example of a simple harmonic oscillator. So let us say consider the case of damped simple harmonic oscillator, and we'll see actually we know how decays are taken into account in such simple system, damped simple harmonic oscillator. So first let us see the classical case. We know that the Hamiltonian for a one-dimensional simple harmonic oscillator in classical mechanics is given by this equation, that is, say, h is equal to p square by 2m, where p is the momentum, m is the mass of the harmonic oscillator. This is the kinetic energy part. Then we have half m omega square q square, where omega is the oscillation frequency, q is the position. There are many typical examples, all of we know. For example, a mass attached to a spring. Okay, so this is the example of a classical simple harmonic oscillator, and from this equation we know the equation of motion would be q dot is equal to p by m, and p dot, which is rate of change of momentum, which is basically the force, that is equal to m omega square q. So at the moment we are not considering without dissipation or damping. This is the equation of motion, and we can get it easily from the Hamiltonian, using Hamilton's equation of motion. Now say the harmonic oscillator is damped, it can be taken into account by the following prescription. So let us consider damped harmonic oscillator. In this case, we can take this into account this way. So q dot is equal to p by m, and we can write p dot is equal to minus m omega square q, and now I will add another term minus gamma p. Gamma is the decay rate, okay, decay rate. So from these two equation, this is going to lead us to the equation of motion. You can just take the time derivative of the momentum, so p double dot, and it is very trivial to show that. You will be able to show that p double dot plus gamma q dot plus omega square q is equal to 0. So this is the equation of motion, and we know that this is the equation of a damped classical harmonic oscillator. So this is the prescription for how damping can be taken into account in the classical context. Now the question is can the same approach be applied to the quantum case, to the quantum mechanical case. So let us see. Well, we know that in the quantum mechanical case, we must have the commutation relation, because these variables, we know that they have to be operator. This qp has to satisfy this commutation relation, so this has to be maintained. Now if I look at the time evolution of this commutation, let us see what we will get. qp is going to give me this commutation. Okay, let me take the time derivative of force. So what is this commutation? We have qp minus pq. So let me expand it. So this will give me q dot p plus qp dot minus p dot q minus p q dot, right? So this is what I will have. Now in the analogy, if I take the quantum mechanical version of the classical equations, so q dot is equal to p by m, and I have p dot is equal to minus m omega square q minus gamma p. So this is what we have, taking the analogy from the classical mechanics case, because now these variables will be operator. So I can now write d of dt qp. Okay, so let me put q dot is equal to p by m. So first term is going to give me p square by m, and then the second term I will have p dot I will just write minus m omega square q minus gamma p. Okay, and then again from this term is going to give me, so I'll just put p dot is equal to minus m omega square q minus gamma p, and here I have q, and the last term is going to give me q dot is equal to p by m, so it is going to give p square by m. All right, So if I do the algebra, so I will just have minus gamma qp minus pq, or I can simply write it as minus gamma commutation between q and p. Now very clear that this we can simply write q of t, p of t. Okay, this is a simple differential equation. So using this, I have the commutation relation between these variables as e to the power minus gamma t, q of 0, p of 0, and we know that this is has to be I h cross, so I h cross e to the power minus gamma t, this is I h cross. So what we see something interesting here. We see that as a consequence of this decay of the commutator, the Heisenberg uncertainty also decays. Okay, and the Heisenberg uncertainty relation in this case would become del q del p is greater than or equal to h cross by 2 e to the power minus gamma t. So clearly, so this is not the case as we know in quantum mechanics. So very clearly we need to look for a different approach. So this is what we see, that classical treatment cannot be extended to the quantum treatment. So we must have to look for a different approach, Okay, now now let us see how one can formulate a simple model for the so-called spontaneous decay of an atom. So let us discuss spontaneous decay of an atom. For simplicity, let us consider a two-level atom. Say the atom has the ground state is represented by kg and the excited state is represented by kT, and the energy difference is say h cross omega atom. Let me take the excited energy state to have energy h cross omega atom by 2, and this ground state has energy say h cross omega atom by 2 minus h cross omega atom by 2. Then we can easily write down the Hamiltonian for the atom, and that would be simply h cross omega atom by 2 sigma z, so z component of the Pauli matrix. Now what happens is that even it may appear that the atom is isolated, but actually it is interacting with the so-called vacuum, and due to the vacuum fluctuation, if the atom is if it is in the excited state, so ultimately it will decay to the ground state because of the interaction with the vacuum or due to the vacuum fluctuation. So generally this can be very easily modeled. The atom is actually put in a, we can consider the atom to be put in a bath of normal modes of electromagnetic field, which could be thought of as plane waves in vacuum, and it is modeled as a set of harmonic oscillator. So we have, this is the atomic part of the Hamiltonian, and then we have a collection of harmonic oscillator which is termed as bath oscillator or simply bath. So we have a set of harmonic independent harmonic oscillators, so this is the bath. Okay, now then there is interaction between the atom and the bath, which can be written as say sigma x, because we know sigma x, this the is responsible for interaction or transition between the excited state and the ground state, or ground state and the excited state, and it is and there is another operator f cap, where as I said, sigma x let me just write here, sigma x induces transition between the ground state and the excited state, or between the excited state and the ground state. On the other hand, this operator f is actually proportional to the electric field at the point of the atom. So it is proportional to the electric field at the point of the atom, at the location of the atom. And we know that electromagnetic field is quantized, and so therefore this f operator can be expressed in terms of the normal modes, and we can write it like this. So say zk, ak, dagger, ak, that's the normal mode, and of course it should have the energy. So we have to write, say, h cross zk, where zk is the coupling parameter. This is the coupling parameter. Okay, now using the so-called RWA under the rotating wave approximation, the Hamiltonian could be this Hamiltonian can be solved. This Hamiltonian can be solved using rotating wave approximation, and I think it should remind you about the so-called James-Cummings model that we have already discussed. So sigma x f under the so-called rotating wave approximation, we can write it as, say, zk sigma plus ak. As you can see, this is exactly the same way we are doing it. We actually employed this technique in the case of James-Cummings model. So this is what we'll have. Okay, now assuming the atom to be in the ground state, in the excited state, while the field to be in the vacuum at time t is equal to 0, we can write the combined system as the atom is in the excited state, or let me just write it up state, or I can simply write it as E, and the field is in the vacuum state. Okay, then this problem can be solved exactly under this condition, assuming it, and it is known as, it was solved exactly, and this is actually the solution is called Wigner solution. Wigner solution. We will not go into the details of the calculation, but I will just tell what they have done. The probability of getting the atom in the excited state and the field modes at vacuum state could be calculated by at some probability, say at some arbitrary time, say t. This is the probability, T is the probability of getting the atom in the excited state at some arbitrary time t. Say it has, the atom is in the arbitrary state psi of t, and we want to find it in the excited state, the atom in the excited state and the field in the vacuum. Okay, so let me do it this way. Okay, so the field is in the vacuum, so the probability would be given by simply the mod square of this. This Wesco-Wagner, they have solved this problem rigorously, and their solution can be represented by a typical plot in this way. Suppose in the y-axis I have this probability of getting the atom in the excited state and the field in the vacuum, and then this is time. So what happens that it will at very initial time, suppose initially it has started from the excited state, at initially at time t is equal to 0, the atom is in the excited state and the so it will start from 1. Initially it will go like this, and then it will fall exponentially like this, and at very large time, this would not be exponential, rather it will follow a power law kind of a behavior, say t to the power minus beta, where beta is a constant. On the other hand, at very initial time, very short time, and at initially this behavior would be actually of the type, say 1 minus, it would be quadratic in time, 1 minus alpha t square, but for the majority of the time it will be exponential. So largely it will this behavior would be exponential decay. So that is what they have found. So as you see, let me write here again, at very short time or very short interval of time, this probability will behave like this. It will decay quadratically in time, where say this is alpha is a constant, and this is the case for at very short initial time, and this is actually, I'm just what the rigorous solution will give us. On the other hand, this probability at very large time or long time, it will go by this power law, where this beta is a constant. So this is the case at very long time. Okay, these two times are actually does not matter much in real atoms, and we can easily keep the exponential decay part only. So we can just focus on this part, so that probability decays exponentially in this way. So gamma is the so-called decay constant. So this result obtained through mathematically rigorous calculation, and it could be represented by a very simple model, and it's very easy to formulate it. So let us do that quickly. Now the situation is that we have this the atom is in the excited state, and we have a ground state like this. So from the excited state, it decay to the ground state by emitting a photon, and the decay rate is, as I said, it is the gamma. So we can set up a equation to see how the probability evolves in time. So the probability that the atom is in the time rate of change of the probability, P dot E, is equal to, as you can see from this behavior, that this is exponential decay. So we can just write it as minus gamma of P of E. So quite clearly from here you see that you will get Pe of t would be equal to Pe of 0 e to the power minus gamma t. Okay, on the other hand, we can also get the probability of getting the atom in the ground state. That would be simply can be found out from this expression, because we know that probability of getting the atom in the excited state plus probability of getting the atom in the ground state should be equal to 1. So using this, immediately you will see that this has to be simply equal to minus Pe dot, and therefore it would be simply plus gamma Pe. Okay, so and we can plot it very simply, very trivially. So this will decay exponentially. On the other hand, it will, from the ground state, probability will increase like this. So this is our P ground probability of referring to the ground state probability. On the other hand, this part refers to Pe. Okay, this is our time. Okay, now what happens if we start with this was a very simple case, because and we see that we have started with the atom to be initially to be in the excited state, and then we analyze it. Now if we assume that case where, say, we start with the superposition of the ground state and the excited state. Suppose initially our system is like this, so the atom is prepared in a state which is a superposition state of the ground state and the excited state like this. On the other hand, the field is represented by a vacuum state. Okay, initially the bath state, or this is the bath state, so this is in vacuum, and this is the atom, this is referring to the atomic state. Okay, now can we apply this procedure that, or this model, the way we have formulated equations, can we do the similar thing for that? Now you see the answer is actually no, because of the fact that Cg and Ce, these coefficients are complex quantities. Okay, because these are complex quantities and there are phase relations, between them. There are phase relations between Cg and Ce. All right. On the other hand, the model that just we discussed, where the probability of getting the atom in the excited state is Ce mod square, and the probability of getting the atom in the ground state is given by Cg mod square. So these quantities P and Pg, okay, they don't take phase relations into account. In other words, the wave function approach cannot be actually applied. Wave function approach is inadequate. Because this approach that, or the model that we discussed, is insufficient. It cannot take into account the phase relations. So the appropriate approach would be, so we need to take the density matrix formalism, we have actually discussed this formalism in our module 1, density matrix formalism, where we can take into account the coherences as well. Okay, in module 1 already we have discussed density matrix formalism in somewhat details, so I would not like to repeat it here, but very quickly we can I can remind you about this density matrix formalism. Let us recall that if I consider a pure state psi, then the density matrix is defined by this way, right, where this is for pure state. On the other hand, for mixed state, the density operator or the density matrix is defined as, this is what we have, this is Pi is the probability, classical probability, and psi I. Okay, so this, I think, if you have forgotten, you can again go through that particular lecture and revise it. And in fact, in many situations we want to focus on the particular subsystem only out of the total system. For example, in this atom plus bath system, okay, atom plus bath system, we would like to focus on, say, atomic state only. And if we want to focus on the atomic state only, then rather than the full density matrix, we can do that by using the so-called reduced density matrix. So reduced density matrix we can utilize, and using the reduced density matrix, what we can do, we can just trace out this bath, and then we can focus on the atomic part only. And we have already discussed about reduced density matrix formalism as well. However, let me quickly refresh you about the reduced density matrix with a simple example. Let us again consider our two-level system, which at time t is equal to 0 is in the superposition of ground state and the excited state. Superposition of ground state and the excited state. This is the atom, and while the field is in the vacuum state. Okay, so the density matrix of the combined atom density matrix for this combined atom plus vacuum is, of course, it is given by psi of 0, get psi of 0, and then this bra psi of 0. Now to get the density matrix of the atom only, we have to trace out the vacuum, and this is basically the reduced density matrix. And if we want to focus on the atom only, then we will trace out vacuum, and we just have to take out trace of this. And if we do that, in fact we did this kind of example in an earlier class in module 1. So if we work it out, then we will be able to get this. It would be mod Cg square, then this state, and then you will have Ce mod square EE, and we'll have these terms containing the information about the phases. Okay, so Ce Cg star Ez. In fact, this can be represented in the matrix form like this. So Ce mod square, Ce Cg star, and we have Cg Ce star and Cg mod square. Now as you can see that the diagonal elements represents the probabilities, contains information about probabilities. Okay, and on the other hand, the off diagonal elements like this, they contained information about the phases, and this is what is actually required. And this was the model that we discussed earlier was unable to take into account, but if we take the density matrix formalism, then we get both the information about the probability and the phases, and this is going to be very important.
Let me stop here for today. In this lecture, we learned about the Transmon Hamiltonian a little bit in more detail. Then we introduced the concept of quantum dissipation or quantum noise, and there we learned that the wave function approach is inadequate. We have to go for the density matrix formalism. Also, we found that the classical treatment cannot be extended to the quantum domain. In the next lecture, we'll see how the quantum master equation approach can be taken into account to understand quantum dissipation or quantum noise. So see you in the next class.